Hi class, this is going to be lecture 6. We're going to be talking about electron configurations. So let me go ahead and pull up the PowerPoint to get started. Awesome, okay. Let's see, start it over. All right, so electrons and electron configurations. So these electron configurations are really kind of, they tell us how many electrons are in each element, and they give us an idea of how they react and some of the properties of the elements. But as we go through this, I'll kind of emphasize what's most important to know. And then also another helpful thing is on the homework, right? The problems that you see most on the homework are obviously the ones that are most important and most likely to show up on an exam. So if you feel like there's a lot of information on some of these topics, I would focus studying and learning the concepts that we practice most in homework and stuff like that. So, all right, so just started out with this little quiz. Okay, let's see how we're doing. All right, so hopefully you paused your video and you could try and answer this. But this goes along with what we talked about last time. So we talked about kind of the basic structure of an atom and how many protons, how many neutrons, and how many electrons are found in each atom just by looking at the periodic table. Okay, so if we're looking at oxygen, right, oxygen is going to be this element right here, okay, number 8. And the atomic number, do you remember the atomic number is equal to the number of protons? Okay, and then the number of electrons is equal to the number of protons when you have a neutral atom, and pretty much they're always neutral if you don't see a charge or anything like that. So we're just assuming this is a neutral atom of oxygen. So the number of electrons is going to be equal to the number of protons, which is 8, right? So C should be our answer, okay? If you're having trouble with that still, just review the last lecture, and the homework problems should also help kind of solidify that. All right, so we talk about electrons. One interesting connection that we'll make is light. So when you see light, right, a light bulb or an LED light or laser pointer or whatever, what's really happening for that light to be emitted is there's electrons in the atoms that are excited up to a certain energy level, and so they absorb energy through electricity, right, is generally it. Like if you have a laser pointer, it has to be powered by a battery. So the electricity excites the element and excites the electrons in that element to an excited state. And then as that electron falls back down to the ground state, it releases energy in the form of light. Okay, so that's where the energy transfer from electrical energy is transferred into the element, which is then transferred as energy in the light, as light energy, sorry. So you don't need to really memorize this spectrum or anything like that. We're just kind of going over an interesting connection and application here. So you may have seen like a prism, something like this. And in this example, what you have is like a light source that's coming in, right? So you might see red with your eye, but then if you use a prism, you can actually divide all the different colors. So there might be some different elements, or sorry, not different elements, but different light that's actually emitted by this. This is strontium. So the electrons are moving to different energy levels and falling back down, like we said, emitting different wavelengths of light. Altogether, you may only see one color, but you can separate them out as well and see all the individual bands. So each band would represent a different energy level where the electrons go up to a certain energy level and then fall back down. So you can, yeah, these individual lines would represent those. And again, this is a lot of just connection, cool application stuff. So you may not see too much of this on homework and tests and stuff like that. So, but it helps us understand these different energy levels, right? So we talked about how electrons can jump. Okay, so they start down here in like a ground state. There's energy that's applied, and then the electron actually moves up to a higher energy level. It's very short-lived, and the electron bounces right back down, and as it comes down, it releases energy, right? So absorbs energy to move up. As it moves down, it releases energy in the form of light, photons. And so the different, if it goes up higher to a higher energy level and comes back down, it's going to be releasing even more energy. So that kind of gets into the idea of these energy levels that we'll be talking about coming up. Here's just another diagram to help you kind of see how different jumps in energy levels can let off different amounts of waves. So you could have all the way from the first energy level to the seventh, and then all the way back down would be like a UV light source, where you can just have purple or blue or yellow. Anyway, you don't need to memorize all these different things. It's just kind of showing you that different jumps in energy release different colors or different amounts of energy. If it's in the visible spectrum, then we can see it with our eye, but it could just be a jump between energy levels that releases a radio wave or a microwave, in which case we can't see it, right? We would need special instruments to pick up those wavelengths. But again, it's kind of interesting application stuff. So this point in the PowerPoint, we're going to talk more about the meat and potatoes of this lecture and what I really want you to glean from this. So here we have these different energy levels. So we talked about energy levels in the last couple slides, okay? So different elements contain different energy levels. And within each energy level, there are sublevels, okay? The sublevels refer to the S, P, D, and F sublevels, okay? Again, energy level is N equals a certain number. Those are just numbered. And then you have sublevels, which are characterized by letters, S, P, D, and F. Within each sublevel, you then have each of these boxes, okay? So each box in any of these sublevels represents what's called an orbital. And then within each orbital, you're going to have 2 electrons. So then you finally have the electrons. And this is like kind of abstract. This isn't something we really see. We only can observe it by different wavelengths that are coming off of an atom. So it's difficult to represent with images. So I recommend when you're learning this, you might feel confused at first, and just press forward, working on the problems and trying to learn the principles, and then you might be able to kind of generate a picture of it in your head. I don't know. Some of these principles in chemistry, like I've said, that it's hard to see, right? So it's hard to visualize. We can only visualize the effects of them and then draw conclusions from that. So we're going to be talking about the theory here. So just kind of bear with me through this, and hopefully by the end, you're understanding it a little bit more. Okay, so each orbital, so again, we talked about all these different energy levels. We have right here, we're just showing 1 through 4, okay? Within each energy level, you have sublevels. Okay, so we'll talk about all these sublevels individually. So we have the S sublevel, okay? And within S, there's 1 orbital. So the S sublevel only has room for 1 orbital. Okay, and this orbital looks like a sphere around the nucleus of the atom. And then it just gets bigger and bigger as the energy levels increase. The way I kind of think of this is, you kind of think of electrons as a single point, right? Like this electron, it's a particle. And then this kind of theory is saying you basically have this electron space that looks like a sphere around the nucleus. And what I kind of think of is like, you know, you've seen like a video where somebody hits a beehive with like a baseball bat or something. And then you have all these bees like buzzing around in this kind of sphere shape or whatever it is. And that's kind of how I think about it. I think about the electrons just like moving around really rapidly, occupying this sphere space. It's really kind of like a probability calculation, but we're not going to talk about it too much, but just kind of think of that the electrons are likely going to fall within this sphere, and really just know that s orbitals are spherical shape is kind of what you need to pull from it. Okay, so again, there's one orbital in the s sublevel, and then each orbital can hold 2 electrons. That's true for all orbitals. One orbital holds 2 electrons. So then you have your p orbitals. Now these are kind of a lobe shape. And so again, you could think of hitting the bee's nest and then the bees flying around, not in a sphere this time, but in a kind of a dumbbell type shape here, okay? So the probability that the electrons within this orbital, or the probability is that the two electrons within each orbital are going to reside in this kind of general area around the nucleus of an atom. Again, the biggest thing to remember is that it's kind of just a 2-lobe shape, and again, all of these increase as n increases, or as the energy level increases, the size increases. And then the p sublevel holds 3 orbitals. So that's different from the s sublevel, right? The s sublevel only holds 1 orbital. The p sublevel holds 3 orbitals. And again, there's 2 electrons. Oh, sorry. 2 electrons in each orbital. And so you can fit a total of 6 electrons in the p sublevel, okay? All right, and the last one we'll talk about is the d orbital. So these ones have really funky shapes. Don't need to like memorize these or anything. Biggest thing to pull off of this is that there's 5 orbitals, 5 orbitals in the p sublevel. And since each orbital holds 2 electrons, you can fit 10 electrons in the p sublevel. Okay. All right. Go ahead and try this quiz here and see how you do so far. Okay. So what's the maximum number of electrons that can fit in the energy level n equals 2? So we can pull this from a diagram that we had earlier in the PowerPoint. But really what we need to remember is at the n equals 1 energy level, we have the s sublevel. At the n equals 2 energy level, we have the s and we have the p sublevels. So you just remember when there's a 1, there's only 1 sublevel available. When there's a 2, there's 2 sublevels available. N equals 3 means there's 3 sublevels available. And so we have the S, the P, and the D. And then N equals 4, which is as far as I'm going to really ask you to do anything with, is 4 sublevels. So that would be the S, the P, the D, and the F. Okay, so we're looking at this second energy level here, right? And within this energy level, we have 2 sublevels. We have the S sublevel, which holds 1 orbital, right? This is that spherical shaped one. And then we also have the P sublevel, which holds 3 orbitals. All right, and these are the ones that kind of look like the dumbbell shape like that. Okay. So and we remember that each orbital holds 2 electrons. So in this S sublevel, there's 1 orbital. So that gives us 2 electrons. And then in the P sublevel, there's 3 orbitals, which allows us 6 electrons. So in the n equals 2 energy level, we have a total of 8 electrons that can fill that energy level, right? So our answer would be D, okay? And then this is just showing it on the diagram, right? N equals 2, we have access to the S sublevel and the P sublevel total of 4 orbitals times 2 electrons per orbital would be 8 electrons in the second energy level. Okay, cool. All right, so we're going to talk about electron configurations now, and if you don't know, if this looks crazy to you, don't worry. But if you did do some reading ahead of time, you might have an idea of how to answer this question. So go ahead and pause it and try and work through this. Okay. So the question is asking which orbitals are filled in a titanium atom. So a titanium atom has 22 electrons. So when we fill energy levels, we're going to be starting from this first energy level, right? We always start from the first, and then we work our way up through the energy levels. So we'll kind of go through this later, but actually I think what we'll do is let's talk about some other stuff before we come back and answer this question. We should have this question again show up later so we can answer it a little better. But answer is D, okay? And again, let's just talk about some of the principles first before I just rush through this thing. Okay. All right, so here's the energy diagram for sublevels. So it's not as simple as just filling the first one, then the second energy level, then the third energy level, then the fourth one. Energy or electrons fill from the lowest energy level up in order to the highest energy level. Or sorry, I shouldn't say energy level. They fill in order from the lowest energy orbitals up to the highest energy orbitals. So the lowest energy orbital is the 1s orbital. Then you have the 2s orbital, then you have the 2p orbitals, then you have the 3s orbital, then the 3p orbitals. Where it kind of breaks down is at this point. You might expect the next lowest energy orbitals to be the 3d orbitals, but what's actually next lowest is the 4s orbital. Or sorry, the next highest is the 4s orbital. And then up from that, you have the 3d orbitals. Up from that, the 4p, 5s. It just gets crazy as we move on, okay? You can try and memorize all this. There's some ways to think about it, but the easiest way to do it, to remember the order of energy of the different orbitals, is just to look at the periodic table, okay? So you can see the different confusion spots that happen as we move through this. All right, here's the best approach. So in that previous quiz question, we said, what is the electron configuration of a titanium atom? So you would look for titanium on your periodic table. So if we pulled up the periodic table, we have titanium sitting right here at number 22, which is right here. Sorry, this is titanium. It's not really labeled on this one, but that's titanium right there, okay? So we know titanium is number 22, which means we have 22 protons and 22 electrons. So if I'm going to draw so the first thing to do when you're answering these electron configuration questions is to draw the orbital levels from lowest energy to highest energy. And if you remember the last slide, we talked about how it can get really confusing. So the way to do it is to look at the periodic table. This is your S block here on the left. So if we just follow, like we're reading the periodic table in order, just from left to right and down the rows. The first spot here is the 2s sublevel, or the 1s orbital. Okay, so we have 1s. Okay, we went through here, and then there's nothing here on the p block, right? Because there is no p sublevel within the first energy level. So then we move down to the next energy level, which is 2s. Okay. And then within the second energy level, we also have the p sublevel. So we go from 2s and then we go through 2p. And remember, 2p has 3 orbitals. So then we keep just moving on down. Now we're at the 3s and then the 3p. We hit those. And then 3 also has a D sublevel, right? But this is where the periodic table is helpful, because instead of putting 3D next, we're actually going to put 4s next. Because by following the periodic table, we can see that 4s comes before 3D. And the 4s orbital is lower in energy than the 3D orbital, which is why the periodic table is organized this way. So now we have 4s, which is next. So this is why the periodic table is helpful for these orders. And then right after that, we have the 3D block, and that holds 5 orbitals. Okay. And if we're doing it for titanium, at this point we can stop drawing because we've already hit titanium. You just keep going until you get to wherever the element is that you're trying to draw the electron configuration for. Okay. So we have 22 electrons. So the next step is to start filling in electrons. And like I said, electrons fill in at the lowest energy orbital first. So we're going to add 2 electrons here, 2 more here, that's 4. And then we're going to start filling in the 2p orbitals. So when you're filling in the 2p orbitals, what you want to do is fill each orbital individually first, and then come back through and add a second electron in each orbital. So you can imagine electrons are all negatively charged. They're going to want to be in separate orbitals before they choose to be in the same orbital. This is referred to as Hund's rule, so you can look that up if you see it in the book or whatever. That's what it's referring to. What it's saying is that as we fill in electrons, we're going to fill in each orbital with 1 electron before we come back and put a second electron in the orbital. And I'm drawing these arrows up and down. It has to do with the electron spin being up or down, or sometimes you see it like positive 1/2 versus negative 1/2. That's not really important for us. We just want to know how to draw these electron configurations. So anyway, if you see me moving across the orbitals before I add a second one, it's because of Hund's rule. And yeah, anyway. Okay, so we have 2, 4, 6, 8, 10 electrons so far. We have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this would be the correct electron configuration diagram for titanium. You just keep going till you hit the number of electrons. And the reason we could stop at 3D is because that's as far as we need to go to put electrons in. What would be incorrect, right, is if you, in your 3D sublevel, if you put both electrons in the same orbital, that's incorrect, okay? Again, according to Hund's rule, they're going to be in separate orbitals before they would be in the same orbital. Okay. All right. So that was showing you how to do the electron configuration for titanium. And in the previous question, I just had a bunch of like numbers and letters all together, right? So the electron configuration written out, all you do is you put the energy level, sublevel, and then how many electrons are in that sublevel. Okay, so we have 1s2 because there's 2 electrons in the 1s. And then if we move on, we have the 2s, which is filled with 2 electrons right here. We have the 2p, which is filled with 6 electrons. And then we have the 3s, which has 2 electrons. 3p is full, it's holding 6 electrons. Sorry. And then the 4s is holding 2 electrons, and then the 3D is holding 2 electrons. So this would be where we got the answer for the question, for the quiz question that we went over. Okay. All right. Again, this is a little abstract up front. You might be like totally lost right now. Let's go through some more simple examples. Hopefully that can help. So let's start with lithium. Okay, so again, we'll walk through a similar process. So we have lithium right here is number 3 on the periodic table. Okay, And to get to lithium, we first go through the hydrogen and helium together is considered the 1s, okay? So we have our 1s orbital. And then the next one we're going to go, so I guess I should maybe draw a line. I don't know. Okay, 1s here. Okay. I'm going to erase that line. It's kind of in the way. Oh no. Okay. Sorry. Okay, we got lithium, number 3. So we went through the 1s orbital up front, and then we're going to go through this second row, which is the 2s orbital. Again, you can see this if you look at that periodic table where it was organized into the different energy levels and sublevels. And once we go through the 2s, we've already have enough to do the electron diagram for lithium because it only has 3 electrons, and we've already gone through the section that holds lithium in it, which is in the 2s, right? So now we start filling with electrons. We have 3 electrons because there's 3 protons. Atomic number is 3. Okay, and then this would be our electron configuration diagram for lithium. If we wrote it out in kind of the more shorthand version, we get 1s2 because there's 2 electrons in the 1s orbital. And then in the second, or in the 2s orbital, we only have 1 electron. So this would be the electron configuration there. Okay, so you can kind of see it here. If you wrote them all out, you'd have 1s, 2s, 2p, right? But we're only going to go up to 2s, so that's all you really need to show. You don't need to show all this other stuff, okay? And then there's the electron configuration for that. One shorthand you can do, it's not super helpful here, but as you move down the periodic table, sometimes you'll see the noble gas, which is this 8th column. So if people will put like helium, tells me I'm actually just going to skip the first part, the 1s, right? 1s2, this right here, is the electron configuration for helium. So we're just going to replace it with helium, and then we'll move on from there. This is mostly helpful when you're talking about like titanium, like we were before. You can put argon, skip all the other stuff before it, and then just do the final electrons. Again, we'll see that more as we move forward. All right, beryllium is number 4. So I'm not going to do this one because it's really similar to lithium. But you have your 1s and your 2s, and then you fill it with 4 electrons, which means you have 2 electrons in the 1s orbital and 2 in the 2s orbitals. This would be your shorthand electron configuration. All right, let's try boron here. So boron sits right here, okay? So first we have our 1s orbital filled because we have our hydrogen and our helium, or we're going past those two basically to get to boron, right? So we have 1s, we have 2s as we go through lithium or beryllium, and then we move into the 2p section of the periodic table, okay? And boron has, so once we have that drawn out, then we look to the number of electrons. So atomic number is 5, so we have 5 electrons. Okay, and that would be the electron configuration diagram for boron. You can also write it out just as 1s2 to represent 2 electrons in the 1s orbital, 2s2 representing the 2 electrons in the 2s orbital, and then 2p1 to represent, you have 1 electron in the 2p orbital. And then you could shorthand it even further if you just did the noble gas shorthand. So you wrote helium to replace the 1s2, and then started with the 2s2, 2p1, okay? All right, showing that there. All right, carbon is very similar, so I'll just kind of go through it. But here's another example of Hund's rule, right? So you're not going to draw carbon. You might be tempted to do this. Okay, you've drawn out your orbitals, and then you say carbon has 6 electrons. 1, 2, 3, 4, 5, 6, right? Again, this is incorrect, okay? You should have the electrons separated out in separate orbitals before, and then fill all the orbitals before you would actually come back and add another electron in each orbital. So again, we kind of talked about that, so that's Hund's rule. All right, nitrogen, they're all pretty similar at this point, but if you want to practice them and then use this as reference on how to do them, that'd be awesome. All right, fluorine, we're getting up there. And then neon would be the final one, okay? So at this point, the second shell or the second energy level is full when you reach neon, okay? So let's talk about sodium. Oh, sorry, I didn't put animations, so we'll just have to talk through it. But again, so sodium is sitting right here on the periodic table, okay? So if we're gonna draw the electron configuration diagram, we're going through 1s, right? We pass through hydrogen, helium. Lithium, beryllium is the 2s. We go through all of the boron through the neon, which is, this area is the 2p. Okay, and then we're moving into the 3s sublevel. And then we have that all drawn out, and then we look at sodium has 11 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, 6 electrons in the 2p sublevel, and then 1 in the 3s. Okay. And then again, if we did the noble gas shorthand, we could say it has a neon core, right? So this right here is equal to the electron configuration for neon. So you can replace that whole thing with just neon in brackets, and then you add the 3s 1 afterwards as a shorthand. So yeah, so that's how you draw the electron configurations. And it's going to be very similar for all the different elements, so keep practicing that. There are 2 exceptions that you need to know, and really it's chromium and copper. These are the 2 kind of weird ones that you need to memorize. So basically what's happening in these ones, let's go through chromium. So if we look at chromium, it's number 24 in the periodic table. It's sitting right here. Okay. So that's 24. So in order to get to the 3D block, if you look at the whole periodic table, you'd see that you go through 1s, you go through 2s, you go through 2p, go through 3s, go through 3p. Oh, I'm running out of room. And then you go, I'm just gonna have to jump up to here, sorry, 4s, and then you go to the 3D, okay, is next. Okay, so for chromium, we have 24 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so this is what you would expect to draw for the chromium electron configuration. It just turns out though that a half-filled 3D orbital and a half-filled 4s orbital is more stable than a fully filled 4s orbital with a partially filled 3D sublevel. Okay. So what that means is that this electron is actually going to jump up into the 3D sublevel in order to lower the energy. So what you actually end up with, so this is incorrect, what you would actually see P 3s 3p 4s 3D, okay? What you actually end up with, I'm just gonna draw lines because it's taking too long. We actually end up is with this, okay? So you have half-filled orbitals in the 3D sublevel and in the 4s orbital. This configuration is actually more stable than the one you might expect. So for all elements, you're just going to follow what we talked about, except for two exceptions that you need to know, which is chromium and copper. And copper is going to be a similar thing, but it's going to have a fully filled 3D with a half-filled 4s is better than a fully filled 4s with a partially filled 3D. Anyway, you can go through copper, but really you just need to know that these two are the exceptions, and it's basically because of that effect that we were talking about. So two exceptions to know. All the rest of the elements are going to be the same though. Okay, same process, I guess. Okay, so we talked about the electron configuration for titanium. All right, so we went through the whole thing, and let's do it again. So we go through the 1s area, and the 2s here, and we go through 2p as we move through here, and we go through the 3s as we move through here, and we go through the 3p as we move through here, and we go through the 4s, and then we move into the 3D, okay, which is where titanium is, so we can stop there. So we go ahead and fill in with 22 electrons. Okay, we got that all done. So if we write this out in the electron configuration, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay. So this was the answer to the quiz question we had earlier, right? The electron configuration for titanium. But if we look at it, this right here is the electron configuration for argon, one of the noble gases. So we can do that abbreviated version and replace that whole thing with just argon in parentheses. And you could go through this and check. But you have a 3p6 filled, which puts you at this position, right? So that's argon. So we have argon, and then we just have to fill in with the rest of it, which is 4s2, 3d2, right? So this would be our more abbreviated electron configuration for titanium. So your answer would be down there at D. Okay, awesome. All right, so that's pretty much the end of that. Go ahead and practice some in the homework, and let me know if you have any questions still on how to do those. Again, it's kind of an abstract principle, hard to see in your head sometimes, but learning how to do those electron configurations first, I think, and getting a solid base of that can kind of help you understand the principle more. But most important thing is being able to do those electron configurations. So again, I just want to remind everyone that I do have office hours Monday through Friday from 10 to 11 a.m. You can find the Zoom link for that on Learning Suite. If you go to the content section, and then there's a tab on the left that says Get Help, and that has my office hours there with the Zoom link, and should have by the time this video comes out, there should be a link for the TA along with her office hour Zoom link as well. So you can come to us if you have any questions while you're watching the lectures or going over the homework, stuff like that. So anyway, I just want to emphasize communication in this class. It's going to be hard since it's online. So if you have any questions, email me or message me on Learning Suite, and we'll try to get it answered. So, all right, have a good one.